sampling distributions. The whole idea behind what we're doing today is you have a population out there, but you don't know what that population mean is, and you don't necessarily know what that population standard deviation is. Our goal is to be able to determine what is that population mean. And we're going to do that by taking samples from the population, looking at that sample mean and comparing it to what we think the population mean should be. Our goal is actually going to be to be able to find intervals, estimations for the population mean. And so we're going to be doing it by sampling. We have to talk about what a sampling distribution is then, so we can sample things. Okay, so a little bit of a review. A population can be thought of as a complete set of measurements or counts, either existing or conceptual. In other words, someone may not have counted it, but you could count it if you took the time to do so. A sample is a subset of these measurements from the population. And a random sample is a sample which is chosen as randomly as possible. In other words, each value in the population has an equal chance of being chosen into the sample. That's a random sample. We try and get as close to a random sample as possible because when your samples are truly random, then your data actually reflects the population data. A statistic is a numerical descriptive measure of a sample. In other words, the mean and the standard deviation for your sample. We use X bar and S for that. And a parameter is the same numerical descriptive measure for a population. Here again, the population mean and population standard deviation. Parameters come from populations. Think P, population, P for parameter. And statistics go for samples. S for statistics, S for sample. That's how you remember it. Now, what we're going to be doing, Chapter 7 is estimation. We'll probably need an H in there. Chapter 7 is estimation. Chapter 8 is testing. And Chapter 9 is going to be regression. Chapter 10, the little bit of Chapter 10 that we do is going back to a chi-square distribution that we're going to be talking about. And Chapter 11, assuming we actually get there, is talking about ANOVA. So that's what we're doing the rest of the semester. What you're going to see is very huge similarities between Chapter 7 and Chapter 8. They're going to be very, very similar. Let's talk about what is a sampling distribution. A sampling distribution is a probability distribution of sample statistics based on all possible simple random samples of the same size from the same population. So you're taking a sample of a certain size. It could be 5, it could be 10, it could be 100 for your sample size. And you're going to do this repeatedly. All of those possible samples that you take are going to give us what we're going to call our sampling distribution. We're going to find out that the sampling distribution has some values that are very similar to the population parameters. The sampling distribution's mean is going to be the same as the population mean, and the standard deviation is going to be proportional to the sample size, square root of the sample size. Now, what we're going to do is to motivate our sampling distribution here, we need to get a sampling distribution. What you're going to do, I have a whole bunch of paper here. You need 1 per person, and you need to tear it up into 9 separate pieces and write the numbers 1 through 9 on each of those pieces. Fold them over so you can't see that number, mix them all up, draw a number out, look at it, put that paper back in, mix it up, repeat it 5 times. So you're going to draw 5 numbers from your sample. And you're going to find the mean for those 5 numbers from that sample. And I'm going to put a place on the board for you to write it down. And we're going to make a histogram of this data so we can see some behavior properties for this sample. So here, go ahead and take a piece of paper. I'll give you most of them over here. Take a piece of paper, spread it around. Each person gets 1 piece of paper. This is your scratch paper of mine. Take a piece of paper, pass it around. Tear it up into 9 pieces. Write the numbers 1 through 9 on it. Watch it. No, 5 times. You can have the same number 5 times.
Yeah, okay, so like we drop by.
When you have your average for your 5 numbers calculated, go write it in the appropriate column on the blackboard. Write your number, your average number. What? And I'll go to 3.49. Oh, there. Oh, yeah, it continues on the other side of the screen. Yeah, these are supposed to go up by 2s. 2.49, 2.5, 4.5.
Wait, guys.
Hey guys, you're gonna have to redo it. I forgot these ones tonight. So, yeah, this is, what did I put up here? 2.49.
Yeah, I'm not gonna do it anymore. Don't hate me.
There's mine.
Yeah, and 4.6.
Anyone else need this?
Did she write? Yeah, no, it is. I actually did.
Okay, did everybody get their numbers written on the board?
Except this table.
Except that table.
Oh, yeah. The answer is 10.
That's all right. Okay, so what you guys have just completed is a sampling distribution. What was the sample size that you did? 5. Your 5 numbers. Your sample size was 5. You had your original population is just the numbers 1 through 9. Okay? What we want to know is what kind of distribution this looks like. Is it binomial? Is it going to be like chi-squared, which I haven't talked what that is yet? Is it going to be approximately normal? So what we're going to do is we're going to make a histogram out of this data. I've already broken it up into classes, so we just have to calculate the data values in each class. We look at the first one. We have 17 data values here. Notice the very first one has 0 data values. And then the next one. This one was 35 data values. This one has 3, and then the last one is 0. So let's draw the histogram for this. We're going to make our classes go from 1/2 to 2.5 essentially for the middle bar, 4.5, 6.5, 8.5, and 10.5. The height on the first one was 0, so I just draw a line. The second one had 17 in it. to do 10, 20, 30, 40. So 17 is a little bit less than 20. Then the next one was 35. That's halfway between 30 and 40. Then we had, 3 on that last one over there, right? Second to last. And then 0 on the last one. Does this look somewhat symmetrical and mound-shaped? Yeah. I mean, it's got a lot more on this side right here than on that side right there. So it's approximately mound-shaped. How do you spell approximately? Almost mound-shaped. We'll go with that. It isn't skewed left or right. It's the middle class there that has a different amount on either side. But it isn't really skewed left or right. So it's almost mound-shaped. It's getting close to being normal. Now, if I had you only do about 10 or 15 samples instead of everybody doing their own sample here, this would look vastly different. It would be much flatter of a distribution. You'd have almost the same number of values in each class because the original distribution is what we call a uniform distribution. There's one data value or 2 data values in each class. From the first one you have 1 and 2, then you have 3 and 4, and then 5 and 6. So the histogram for the original data would be uniform. It would be a straight line across it. Looks like a box. How come this one doesn't look like a box? You guys remember a theorem we learned? It's in section 6.5. It's called the central limit theorem. If you have sample sizes greater than or equal to 30, your distributions are approximately normal. The sample size in that question is not the 5, but the number of samples that I do. I did approximately 70 samples in here. We're missing some people, so it's not exactly 70. But it's more than 30 samples, so my data should be approaching a normal distribution. It's a little bit more mound-shaped. The more times you sample something, the better your results are at representing your data. And the closer to a normal distribution you get more of the outliers cropping in and stuff like that. So this is almost mound-shaped for this distribution. Do you guys understand what a sampling distribution is? It's exactly what we did here. It's a combination of all possible samples of the same sample size that you could take from the data and the results from each of those. That is the end of section 6.4. Let's go and look at section 6.5. Section 6.5 is all about the central limit theorem. The central limit theorem has 2 statements. One of them is for a normal distribution, and one of them is for any distribution out there. So for the normal distribution, if you let x be a random variable with a normal distribution that has a mean mu and a standard deviation sigma, the sample mean corresponding to sample sizes of n, size n, taken from the x distribution, the following are true. The x bar distribution is a normal distribution. In other words, the distribution of all the averages, that distribution that we wrote on the board, is approximately a normal distribution. The mean of the x bar distribution is the mean of the original distribution, and this is quite amazing because this is the average of averages. The average of the averages is the original average. It stays the same. The standard deviation is proportional to the square root of your sample size. Sigma over the square root of n. Now, that's for a normal distribution. if you don't know your original distribution is normal, so X possesses any distribution, it still has a mean, mu, a standard deviation, sigma. The sample distribution X bar, this did not get spelled right, based on a random sample of size n, will have a distribution that approaches the distribution of a normal random variable. So it begins to look like a normal distribution as n increases without limits. So as n gets bigger and bigger, you get a normal distribution. The mean is still the same, and the standard deviation is still the same. But for this distribution, we have to have n large. Large, in our case, is going to be defined to be greater than or equal to 30. It isn't always true that it's greater than or equal to 30. Sometimes it has to be much bigger than that. The only way to know is to make a histogram of it. Once you start seeing it looking mound-shaped and symmetrical, you know you've got enough samples. Okay, so what you need to take away from the central limit theorem. Your homework questions are going to ask you, what if you know anything about the original distribution? If the sample size is 16 and the original distribution is normal, then you know the X bar distribution is normal. But if your sample size is 16 and you don't know the original distribution is normal, you can't say anything about that sampling distribution for X bar. It's not until n gets bigger than 30 that you can say anything about the sampling distribution for X bar. And that's what's important from this. So this is our rule of thumb. N greater than or equal to 30 is considered large enough, generally. Now the procedure for the homework problems. Given a probability distribution of X values, where n is the sample size of each sample, mu is the mean of the X distribution, and sigma is the standard deviation of the X distribution. If the X distribution is normal, then the X bar distribution is normal. Even if the X distribution is not normal, if the sample size is bigger than 30, then the X bar distribution is considered normal. And this is our formulas for calculating the mean and standard deviation for each of these. They're not hard formulas. A couple of definitions, and then I'm going to do some examples. A sample statistic is unbiased if the mean of its sampling distribution equals the value of the parameter being estimated. In other words, if mu X bar is equal to mu, that tells you that it's unbiased. So X bar is an unbiased estimator because I have these two equal by the central limit theorem. The standard error is the standard deviation of a sampling distribution, and it is this formula right here. Sigma X bar is your standard error. So they just gave them some names. That's all they did. Let's look at some examples. It says, let X be a random variable that represents white blood count per cubic milliliter of whole blood. Assume that X has a distribution that is approximately normal. As soon as they told me the X distribution is approximately normal, I know the X bar distribution is approximately normal. It gives me the mean of 7,500 and a standard deviation of 1,750. It says a test result of X less than 3,500 is an indication of leukopenia. This indicates bone marrow depression that may be the result of a viral infection. What is the probability that on a single test, X is less than 3,500? It told me it's approximately normal. So this is normal CDF. What is the low value for this? A very small number, right? So negative 100. What is the upper value? 3,500. The mean is 7,500. And the standard deviation is 1750 over the square root of 1, which is just our 1750. When n equals to 1, it doesn't change anything. And you're just going to calculate that. So let me get my calculator up. By the way, I put the links for the normal distribution up on eClass 2 if you're needing that. Okay, so our distribution, go down to our normal CDF, which is number 2. And then we were using negative 100. The upper limit was 3,500. Oh, I got 2 3s on it. The mean was 7,500, and the standard deviation was 1750. So that gives us 0.011 rounded to 3 decimal places. That's about 1.1%. So that doesn't happen very often. Okay, that is something we did on the last homework. You guys should have been able to do that from the homework for section 6.3. Now let's look at number 2. It says, suppose a doctor uses the average X bar for 3 tests taken about a week apart. What can we say about the probability distribution of X bar? So in this case, we're going to have n equals to 3. And it says, what is the probability distribution for X bar? Notice the original was approximately normal. So no matter what the sample size is, the X bar distribution is approximately normal. And then we have to find the probability that X is going to be less than 3,500 on these 3 tests. X bar is smaller than 3,500. What is going to be the mean for the X bar distribution according to our central limit theorem? It's going to be the mean of the original one, which is 3,500. This is by the central limit theorem, CLT. Yeah, I got it backwards, CLT. And then what is the standard deviation? It's the original standard deviation divided by the square root of n. So it's 1750 over the square root of 3. So let me calculate that. That's going to be 1010. I'm going to use 2 decimal places, so 1010.36. And so we're looking at normal CDF. Here again, minus 100 for the low value, 3,500 for the upper value, 7,500 for the mean, and then 1010 point, I think it was 36 for the standard deviation. Yep. We're going to plug that into our calculator. The negative 100 is the same, the 3,500 is the same, the mean is the same, but this becomes 1010.36. That becomes what value? What does that negative 5 at the end mean? Yeah, I got 5 zeros in front of that 3 after the decimal place. So that is going to be equal to 1, 2, 3, 4, 5, 3. But if I want to round it to 3 decimal places, what's my answer? 0. Okay, we got our answer for number 2. Notice the difference is what you plug in for your standard deviation. It becomes the standard deviation divided by the square root of the sample size. That's what you plug in for your standard deviation. Everything else is just like what you did in section 6.3. Nothing changes other than that. Now let's compare our number. Let's look at number 3. It says compare your answers to parts 1 and 2. How did the probabilities change as n increased? Did they get bigger or did they get smaller? They got smaller. So the probabilities decreased. If a person had a mean average less than 3,500 based on 3 tests, what conclusion would you, as a doctor or nurse, make about that person? They have leukemia. That's a question someone has to answer relatively on a daily basis. Are you sick or not based on your test results? But that is also why most doctors will do repeated tests, because one test doesn't tell you nearly as much as multiple tests. You may think it's a waste of your money, but you can get false results on one test. But the same result over multiple tests is much more substantial. Any questions on that? Okay. Let's look at another example. This one's just like your homework. I think it's like your 4th or 5th homework problem. It says consider an X distribution which is approximately normal with a mean of 100 and a standard deviation of 20. If specifications for a research project require the standard error of the corresponding distribution to be less than or equal to 3, how large does the sample size need to be? In other words, find n. Well, it said standard error. What's the formula for the standard error? Sigma over the square root of n, right? Standard error is the standard deviation for the center limit theorem. What is our standard deviation? 20. And we are looking for n if the standard error has to be less than or equal to 3. So I'm going to plug in a 3 for this right here, and you get 3 is equal to 20 over the square root of n. Solve it for n. I'm going to multiply both sides by the square root of n. And I have 3 square root of n is equal to 20. I'm going to divide both sides by 3. And I have the square root of n is equal to 20 over 3. And then let's square both sides. So I get 400 over 9. Let's ask our calculator what 400 over 9 is. It's 44.44. Now, look what I put in bold here. It says round to the next whole number if you get a decimal answer. So we're going to use n is equal to 45. Don't round down because it's less than 0.5. Round to the next whole number. Rounding up always ensures you will have your standard error less than or equal to your requirements. If you round down, you might make your standard error bigger. So always round up. N equals to 45 in this case. Any questions on that? You have a homework problem just like that. Can you do that on your homework? Yes, that's the right answer. Just in case you're wondering. Okay, this one's a checkpoint exercise. This is just like the first example that I did today. So write the basic information down. Well, I'll put the formulas on this page. The mean for the x-bar distribution is the mean of the original, and the standard deviation of the x-bar distribution is the standard deviation divided by the square root of n. The first one says an 18-year-old, so that's n equals to 1, so you don't divide by the square root of 1, that just stays the same. The second one has n equals to 9. So go ahead and see if you can do this question. Hey guys, watch this. On number 1, it says find the probability that an 18-year-old man is between 67 and 69. So that's going to be 67 is less than or equal to x is less than 69. X is an 18-year-old man. Now, in that case, you're going to use just the mean of 68 and the standard deviation of 3. On the second one, it said 9 18-year-old men. So you're looking for the probability 67 is less than or equal to x bar is less than or equal to 69. It's not x, and the second one is x bar, which means you have to use the mean mu x bar is equal to the same mean you had before, which was 68, but your standard deviation for x bar is the original standard deviation over the square root of 9. So you're still using your normal CDF distribution, but what is the difference? For the first one, you have normal CDF. What's the low value for that? 67. What's the high value? 69. What's the mean? 68. Standard deviation? 3. For the second one, you use normal CDF. What's your low value? 67. High value? Mean. Standard deviation? 1. You see what the difference is? You are calculating the average of the 18-year-old men. And when you do that, you have to change the standard deviation right there. That is the only difference between the two of them. Okay, make sure you're rounding your answers to 3 decimal places when you're doing that. When you're done, make sure your names are on your papers.